What is a linear transformation? X, Y. Is this one a linear transformation? No, because it has to pass through 0. Excellent. We remember this stuff here. Let's go here. A linear transformation is a warping of the fabric of space so that any couple of parallel lines in the domain are mapped into parallel lines in the codomain. How many of you saw this definition here? I saw and I understood it, never saw it. I think I understood it. Okay. I have a domain. I have portrait. And I take the portrait and I warp it. True? It's like fabric. For the people that do not see me, I've got my hat in my hands and I stretch it. Okay, it's a warping of space. The operation of stretching is a warping of space, and I start from a certain condition and I arrive at a final condition. True, starting condition, final condition. True, and the transformation is a transformation in general. Okay, physically I am stretching space. How much are we together up to now? Perfect. Look at this specific, this is a specific stretching. True? If I take this line and this line, in the domain, are they parallel? Yes. True? If I look in the codomain, how do they look like? Now I'm gonna draw them in a bad way, but I hope they are the right ones. Yeah, they are kind of the right ones. I start from objects that are parallel and I end up with objects that are parallel. You see it? Actually, for any couple that I choose here that are parallel, I end up into a codomain where they stay parallel. Do you see it? This is a linear transformation. A linear transformation is a stretching of space that preserves parallelity. How do you call it? Parallelism. Sorry. Together? Do you see it? Do you see that this is a stretching that preserves parallelism? What's out? It has to be for any parallel lines. Okay? Here, for convenience, we have what? We have a grid and the mapped grid. This is a visual aid for you to see that actually this holds. But we have to imagine that whenever we do the operation of stretching the domain into the codomain, this stuff here, this additional grid, is not existent. Okay? Together? With a caveat. I redo it here. What's this one? X, Y. What's this one? What's the name? Linear map? No. We do not have only the parallel is parallel. 0 is 0. We need to have also something for which the 0 of the domain gets mapped into the 0 of the codomain. The 0 of the domain gets mapped into the 0 of the codomain. Do you see it? Okay, together. Otherwise, if we have only parallel lines, this one I should fix it actually. Because typically I kind of assume it as obvious, but it's actually not obvious. We might have also something for which we have a affine transformation. Preserves parallelism, but shifts the 0 around. Together? So linearity is not only affine, it's affine plus 0 in 0. How much are we together, people? 1, 2, 3. Other questions? This one. Is this one a linear transformation? Yes, no, I do not know. Discuss. Okay, people, what would you say? What would you say? Everybody says 1, true? Why? Because in a certain sense, I'm putting you a grid. This visual grid is kind of helping you decide, true? Because somehow this line here and this line here, I see immediately that they are like this line here and this line here, true? And they are parallel. Now, we might have some warping inside here of the cell that might destroy, so the visual aid is kind of incomplete, but I'm not tricking you. You kind of see that it's a linear stretching in the sense that it's a stretching and a rotation, true? And rotations and stretchings are actually linear operations. If it is a linear stretching, stretching that is uniform. Okay? Interesting thingy. Look at the notation, how I'm going to use this notation essentially throughout the whole course. This and this, you see that they are different with this and this, true? They are visual aids. What am I indicating? I'm indicating that this element, that is actually this point, gets mapped into this point, and this point gets mapped into this point. Essentially, whenever I define a grid by means of 2 elements here, I'm going to define the mapped grid. True? Excellent. I could have chosen also this and this. True? We will see very soon how this implies changing bases. This one. Is it a linear transformation? Yes. It's a rotation. Preserves parallelism. True? Stretching. Flipping. True? This is a flipping. True? You see? This one. Linear? Yes, no, I do not know. Definitely not. True? Are we together, people? This one? Definitely not. In more dimensions is the same. And watch out. The examples that I'm doing here are examples that are kind of forced by the fact that whenever I draw something, drawing things in R2 is easier than drawing things in R3, R4, etc. This object here, plus 0 gets to 0. The stuff here is also whenever we change dimensions. If I take, I think I forgot to put it here, but it's okay. I will make it. I will make it. Where am I? If I take the Mona Lisa and I compress it sideways so that I eventually get only a thread, we are going from R2 to R. True? True. Here, it's the parallelity becomes kind of equidistant. If I start here, 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 where do I go here? Depends on what I'm taking. If the compression direction is this one gets into a point. This one becomes everything. True? Do we see it? Do we see it? 1, 2, 3. Do we see it, people? This is very important. Perfect. Assuming that this is the direction of stretching, of compressing, such that this is going to be the kernel. We are going to see it very soon. In a certain sense, parallelity here means two stuff that is distant a certain amount, and those stuff that are distant twice the amount. This gets mapped into a point, this gets mapped into a point, this gets mapped into a point. I might have a stretching here. In a certain sense, if this is 1 unit and 1 unit, this and this has to be 1 unit too. Are we together? If I compress into a line and then stretch the line, this parallel means that in a certain sense the grid is preserved. Do you see it, people? It's more difficult to say than to visualize. The same is from R3 to R2. R3 to R2. I have a line, parallel. They might, in general, become line and line. We need to preserve the parallelism. Okay? Plus 0 gets mapped into 0. Okay? How do we feel, people? No, it's too difficult. No, not related to the stuff that I want. How do we feel? Very fine? Not at all? Kind of. Are there questions? Yes.
Calculating the transformations, does have to be from R2 to R2, or can it be from R2 to R and still getting?
It can be from Rn to Rm. The two questions that you've got to ask yourself is parallelism preserved? Is 0 from the domain get mapped into 0 of the codomain? So it's completely general.
So if you have two parallel lines in R2, and if you have a linear transformation such that it was just a point, like you said,
You've got to preserve the spacing. Let's remake it. So let's go here. This one becomes a line, stretched line. Imagine that these everything gets compressed in this direction. Okay. Imagine that everything gets compressed in this direction. If I take this line and this line, what do I get in the codomain? I get this line and this line. True? They are on top. You see everything. True? Together? If instead I take this line and this line, they become 2 points. True? They become a point here and a point here and a point here. True? This stuff is compressed in our image. Are we together, people? 1, 2, 3. Perfect. If I take also this line here, that becomes this stuff here. Here I've got 1 unit of distance and here 1 unit of distance. True? Here I've got 1 unit of distance and 1 unit of distance in the codomain. True? If this green point here would have been here, the parallelism wouldn't be preserved. You see that from a logical perspective, it's kind of a stretching. True? A nonlinear stretching. Perfect. Are there other questions about this, people? How do you feel? Are we there? Yes.
With this thing you said, it now tricking me a bit because we should guarantee that there is still parallelism, but not that there, for example, two lines maintain the same distance, right? If we talk about going from R2 to R2, so if we're talking to going to R2 to R1, why should the distance be the same?
Okay, so I have this one, and this one. And then I go in R2. I have this one, and now, sorry, this one. And now imagine that this one, the head, it gets stretched so that we go here. These and these are equidistant. These and these are not. True? You see? Eventually it boils down that you have to preserve also kind of this tessellation. It's a tessellation. We are going to see it very soon. It's kind of a form. Let me do it this way. To have linearity, you kind of have to be able to tessellate the domain with some tiles. The first tile will become another tile. And the way that you tessellate the domain with the main tile, you have to have the same way of tessellating the codomain with the same tile, the transformation of the main tile. We are going to take it very, very often. This viewpoint here eventually is the same of parallelism. It's not the formal definition, though. Formal definition is parallelism. And all the properties boil down. The stuff that I'm saying up to now is they are kind of properties that boil down from the assumption that you have linearity, parallelism. Question. You take your floor and you have a pattern and you repeat the pattern so that you cover up all your floor. You see, this is the kitchen, and you've got a tile made of squares, and you tile up the squares. Then you take the first tile, you stretch it. Do you have the same pattern in the codomain? If so, then it's a linear transformation. Do you see it?
Can you have a transformation from a lower dimension space to higher dimension?
Absolutely. I have this painting, and a painting is in 2D, true? And I show it to you in front of you, and I'm moving it in 3D.
So
Sure.
you basically put the plane
Somewhere. Okay, other questions? Yes.
Is it interesting to talk about if the first domain was stretched and the other one was just a line? What would happen if you took something in the codomain, not on that line, and drew it back to the stretched out one?
I'm not sure that I understood the question. So you've got a domain that has got a dimension that is bigger than the codomain. Okay, so this one is not this one, but let's say only this line here, we are compressing in this direction, let's pretend. Okay, and then you want to take a point in the codomain and go back.
Yes, but the point is not on that line, it's on
Here.
somewhere else, yes.
But then the codomain is actually R2. It's about invertibility. We are gonna see. We are gonna see about this. It's about invertibility, the transformations, and the range of the transformations. We are gonna talk about the range and rank, and it's a very meaningful thingy. I will introduce it in due time because there's an example about a dot x dot equals to ax, but we see it in due time. There is the situation for which you got the map where you go, and then you might take something else. But then in this situation, you are assuming that the codomain is R2 and the range is R1. We are gonna see it. We're gonna see it. It's gonna be, let's make it this way. If whenever we discuss about range of a map, this is not clear, you tell me again. Okay, perfect. Other questions, people?